Hi, this is David. Let's take a look at Chapter 11, Correlations and Copulas in John Hull. And we'll start with, in this list, one of the more important learning objectives is the first one right out of the gate. Define correlation and covariance and differentiate between correlation and dependence. So the formula here for the correlation coefficient is, and that is denoted by Greek rho, almost always the case. Hopefully that numerator's familiar. That's the covariance. The expected product minus the product of expectations. That's our formula for covariance when we have expectations. And that's going to be divided by the product of standard deviations or volatilities. So here in more familiar form gets us to one of the most fundamental formulas in the FRM. You absolutely do want to have this memorized and be ready to use it. The correlation coefficient, Greek rho, is equal to covariance divided by the product of the standard deviations. And the covariance is typically a number that's not intuitive to us naturally. So by dividing by the product of standard deviations, we render the covariant unitless. So this is another way to look at this, is that the correlation coefficient is not so different from the covariance. It's taking that covariance and standardizing it into a unitless number that lies between -1 and 1.0. And so this next part is important. Differentiate between correlation and dependence. Really important idea. And that is to say, correlation is not dependence. I've tried to illustrate it graphically here, but here we have the region of variables that are independent. There's no relationship between them. They are independent or not dependent. If it's not independent, then there is a relationship, and most generally we say the variables are dependent or have some dependence. But that's a broad concept, including nonlinear relationships. So it includes, but is not limited to linear relationships as measured by correlation. So here's that key idea. Dependence does not imply correlation. Correlation, if variables are correlated, that does imply dependence. And graphically, this is also from the learning spreadsheet that's got several sheets in it if you want to take a deeper dive. But graphically, I've just illustrated that here as well. Notice visually, I think we can agree that in all four cases there is dependence or some relationship between x and y. In this case here, it's a perfect relationship because I'm just plotting a simple equation here. Y is a function of x, and the correlation coefficient here is a perfect 1.0. So that's a perfect correlation. They are correlated and they are dependent. But look down here in the bottom panel. There is a relationship. There is a dependence between x and y, but because there's a dependence, we cannot say that they are correlated. And in fact, mathematically, because correlation is a measure of linear dependence. Mathematically, in fact, the correlation is 0 or pretty close to 0 in both cases. So I hope that makes a persuasive case for the difference between those terms. And then before diving any deeper, I do just want to revisit here mathematically how we get to the correlation coefficient. And that's because I generated here a series of 20 random pairs. I took out the middle here to save space, but this should say 18, 19, and 20th observations. They're plotted over here in blue dots. Or sort of a typical plot of a return of a security against the market index. So here's R sub I against R sub M, the market or the benchmark. Those are in blue dots. And then I just had Excel draw me an OLS, ordinary least squared line through the lines. It gives me back the function. Also returns the, probably can't see it, the R squared, also called the coefficient of determination. In a univariate regression, the R squared is the square of the correlation coefficient. So, and that's true here. If we take the square root of the R squared here, 0.389, we do get the correlation coefficient. Put another way, if we square Greek rho, or small r, we're going to get the r squared for the linear regression. Okay, but in terms of calculating that correlation, I have a series of pairs, and here in the third column, it's a cross product, right? We're taking the observation, the return of 1%, minus the average for the series. So that's a difference multiplied by that same difference here, the observation minus the average. The product of those two differences is the cross product. We have a series here, in this case, of 20 cross products. The average of those is the covariance. And as I suggested, not naturally an intuitive number to us. But if we divide it by the product of the standard deviations for each of these variables, we're going to standardize this covariance into something that is more intuitive to us. And in this, you can see here, it's 62.37%. On that actual spreadsheet, I've also got an Excel performing the calculation, giving me the exact same result. So that's the fundamental math that goes into the correlation calculation.